This is the bike wheel sinusoidal function with me, Ryan, and Ava.
Okay, so our word problem. Ryan is on a bike ride. He placed a piece of tape on the edge of the wheel to observe how it traveled as he rode his bike. How does the height of the tape change as he travels? The relationship in our word problem is how distance traveled affects the height of the tape from the ground. As the bike moves, the rotating wheel change the height of the tape. In our equation, y will equal height in inches and x will equal distance traveled in feet.
So we found this nifty model online of someone doing a similar bike tire trig function, and they have a cool machine that they can use to graph each point as the wheel's moving, following the yellow light. And if we watch them do it really fast, he's adding points following this yellow light. And if we look over here, we can see how it's slowly creating a sinusoidal function. And that is basically what we were doing in our thing, but we were following a piece of tape on Ryan's bike.
The way we simulated this was I placed a piece of tape on my bike wheel and I rolled it along, and every 5 feet I would measure the height of the tape from the ground in inches, and this table shows that. So at 0 feet we started at 0 feet, and we started with the tape at 0 inches, so on the ground. And then as we rolled, we all went all the way up to 40 feet. And as you can see, it changes as the wheel rolls.
And the diameter of Ryan's wheel was
26 inches.
So for making the equation, first we definitely took into account how many inches the wheel was in order to find the circumference. Since the diameter was 26, we just did the basic diameter times pi to find that the circumference of the wheel was 81.6 inches. And then from there, we obviously knew that the maximum height that the wheel could reach was 26 inches because that was the diameter. And then the minimum was 0 inches when it was on the ground.
The frequency, or the period, actually, as we know, it would take one entire rotation of the wheel to get it all the way back to 0. And we knew to do that, the bike would have to travel the circumference of the wheel, which is 81.6 inches. Therefore, the period of the sinusoidal function would be 6.8067 feet, or 81.6 inches. And from that, we could also calculate the frequency by putting 1 over the period, and we got 0.147 feet. The amplitude as well, we knew that the maximum height was 26 inches. Therefore, the period would have to be half of that, since the midpoint would be halfway between the maximum and the minimum. Thus, the amplitude would be 13 inches, or negative 1.083 feet. And from there, we found the equation: 12 times negative 1.083 cosine, cosine within the parentheses 0.923x plus 1.083. Yes, the A shift 1.0 plus 1.083 was to ensure that the graph started at 0 when we were at a y value of 0 when we were at x value of 0, and the 12 is to convert the feet to inches.
This is our graph, graphing our equation. And as you see, as Ryan was talking about, we shifted it so it started at 0, so that it would accurately represent how we measured it, because our starting value was 0, and it goes all the way up to 40. So we had to make sure that it started at 0 in order to accurately represent our data.
So when making our prediction was, what will the height of the tape be after Ryan has traveled 1 mile? We used the equation and plugged in 5,280 in for x, because that is the amount of feet in a mile. And we got y equals 25.68 inches for the height of the tape.
So that was our trig function and how it applies in real life to bike riding, which everyone does. So really helpful.